Good evening. So today we are now continuing with our third week, and here we'll cover on the sensing technologies. Now today in the lab you have physically seen some of the sensors. So we'll delve on different kinds of sensors today. Okay. So basically here we'll be talking about two types of sensors, conventional sensors and the sensors based on smart materials. Now both are equally important, reason being that we must understand each type, then only we'll be able to see the importance of the advanced sensors. So let's first do with the conventional sensor. So when we say a sensor could be used for measuring a static response or dynamic response. So here these sensors, for example the electrical strain gauge, theoretically it can be used for both static as well as dynamic measurements, but it shows inferior performance in dynamic measurements. Now the vibrating wire strain gauge, it's used for static measurements only because its principle is also vibration based. So basically here we have to plug the wire, pre-tension wire, into vibrations and then we measure. So here this vibrating wire strain gauge is suitable for static measurements only. Accelerometers are suitable for the dynamic measurement. Acceleration, of course, it is implicit that we are dealing with some dynamic phenomena. Then we have the sensors based on smart materials. So some of these are static, some of these are dynamic. So we'll view each one of them. So electrical strain gauge you have seen. Today I showed you in the video. Basically it consists of these kind of metal foils which are positioned like this. So what is here, this kind of structure is there of a special alloy. So this alloy is such that it has negligible effects of temperature variation and other issues, but of course there are still temperature variation etc which are to be accounted for. So basically this is bonded on the top of the surface of the component which we are choosing for measuring strain. So if the member is undergoing some strain, so naturally these grids, they will also undergo strain. So here it uses the simple principle of physics that the resistance of a conductor, it undergoes change when stress is applied across the conductor. So that is the simple principle. So this equation itself exemplifies that the change of resistance, the relative change of resistance is directly proportional to the strain. And this is represented by this gauge factor. So this gauge factor is constant, and usually the manufacturers provide this gauge factor. For the sensors which we are using in our lab, it's around 2. So its advantages are that it's very low cost, you can use in any number without incurring high costs, it's easy to install and handle, just a simple Wheatstone bridge circuit. So you may recall in your school physics that you may have done experiment on Wheatstone bridge. So here if we are trying to measure this resistance, and if we are keeping all others same, so if this is the one which is bonded on the structure and if it undergoes change on account of strain, what will happen? Immediately there will be a current flow. So the Wheatstone bridge will be unbalanced and there will be a current flow and there will be a voltage generated, and that will provide us a measure of the change of resistance. So there are now data loggers in the market which can do this measurement automatically. So we just show you some of the examples. So all of these are case studies done in our lab by BTech students. So this is a frame. So basically here at these junctions, for example 1, 2, we have bonded a pair of these strain gauges on the opposite surfaces, the extreme left and extreme right. Similarly on the beam we have on the top and the bottom. So like this, at key junctions we have bonded the strain gauge in this fashion in pair. Now why do we need in pair? If you want to eliminate the effects of the axial stresses, that is, if you want to just purely measure the bending, then you must have two. And similarly, if you want to eliminate bending and if you want to just purely measure the axial strength, then also you need two. So this is what configuration is necessary if we want to measure the axial and the bending effects separately. We'll just show you by the equation. So here are the measurements. So what we have done is that in this structure, let's say some unknown load is acting and we don't know. That's what happens in the structure. At the time of design, we do estimation of the loads, but what actually comes on the structure we don't know. Now here, if we install strain gauges, then what we can measure is we can measure the axial force in these two columns, and that sum of the two axial forces, it will tell us how much load is acting here. This is the external load. So that's what we have done here. So here we are now comparing that this is the actual load applied, and we have also estimated the load from the strain measurement, and then we have estimated the actual bending moments. So we'll just wait for 1 or 2 slides where we just disclose a very simple principle of structural analysis that we use. And finally, if we have the bending moment with us, then simply by the double integration of the bending moment, we can even get something like deflection. So this is what is possible by strain measurement. So similarly, we can do the monitoring of the RC structures also. So for example, here we have this reinforced concrete structure, and if we are doing some minimal measurement, say we are measuring strains at the top and the bottom, so either we can measure the surface strain on the top of the concrete, or alternatively we can bond these strain gauges to the rebars and we can measure the strains at the rebars. So this is also possible. So this rebar bonding is much better as compared to the other one, because here steel strain gauge interface, the connection, the bond is very good, and then the rebars, they are now inside the structure, the concrete, they are surrounded by concrete, so they are well protected. Okay, so that's what we have done here. If we do strain profiling, and we assume that strains along the depth, they are linear, then we can obtain these stress diagrams. And once we have these stress diagrams based on the available stress strain diagrams of concrete and steel, then we have at our disposal the compressive and the tensile forces. And once we have the compressive and the tensile forces, it's just the summation of the two algebraic summation that will give us the axial force, and we just need to take moment of these forces, and that will give us the bending moment. So here we are just displaying here how we obtain the total compression force, and by this we can even obtain by integration the depth of the centroid of the compression force. And then all we have to do is take moment of the compression and the tension forces, and that will give us basically the bending moment. So here are the comparisons. So here what you can see is the skeleton, the steel rebar skeleton, and the strain gauges, they are bonded here. So these are the electrical strain gauges, and then they are covered with silicone rubber, white silicone layer for protection purpose. And then here are the results. So what we have done is, from the strain measurements, we have tried to estimate how much load is actually acting on the beam. So results are quite comparable. and then these can also be extended for other shapes. For example, here this was a small tender shape structure used by one of my former BTech students to estimate the external load acting on the structure. Because we have seen that structural health monitoring means we have to look for what are the external loads, number one, and number two, what is the effect on the structure. Is the structure still the condition is as close as the pristine condition, or is there any damage? If there is a damage, then what is the magnitude of damage, that is severity, what is the location of damage. So these two things, they are required. So if we install strain gauges, at least the first purpose we can very easily solve. We know the loading, the loads that are acting on the structure. For example, we are bonding strain gauges on the top and the bottom surfaces, and then using the Euler-Bernoulli equation, then we can write the expression for the overall strain. For example, if there is tensile force also acting, that is axial force, and then the bending moment, then this is how we can express the strains in terms of the axial force and the bending moment. So here our sign convention is that tensile strain we are considering positive, and that's why this sagging moment, it will give rise to here compressive strain, so that's why we have minus here, and for the bottom we have plus here. So if we just combine these two equations, we can express from the measurement. If we have the measurement of the bottom and the top strains, we can very easily estimate what is the axial force and what's the bending moment at this particular section. So this is what the principle used in the diagrams or in the results which I had showed for the previous structures. All right. And in fact, we can go a step further. If we use the simple equations, slope deflection equations, then we can even estimate from the measurement, we can estimate the rotations, the end rotations. So this is also theoretically at least possible. So if we know the loading on the structure, and if we are able to estimate the fixed ended moments, then we can obtain the end rotations. So slope. Yeah, so drawbacks are, now this would be not just limited to the electrical strain gauges. So we will have to deal with wires unless we have a wireless system. So generally electrical strain gauges, they work with wiring. So if we have n number of strain gauges, that means we have to deal with n wires also. Then they are prone to electrical noise because they are using the electrical principle. So if there is any electromagnetic interference, then that will also lead to noise. And in fact, if we are doing dynamic measurements, then that noise will make a higher impact. Then they are prone to deterioration by water, because water, it causes damage to these strain gauges. That's why if we are inserting these strain gauges, if we are installing on the rebars in reinforced concrete structures, then we have to be very sure we have to protect them, else even the atmospheric moisture can spoil them. Then they also suffer from decay if loaded for prolonged periods. If, for example, you are doing a test and you have just sustained some loading and you have left it. So after 1 week, if you come back, there is you will see the phenomena of what is the stress relaxation. Even if this phenomena is not on the component to be monitored, but the strain gauges, they will exhibit this kind of phenomena, and you will see fluctuation in the measurements. So they are suitable for short-term static monitoring, they are very good, but for long-term monitoring they are not good. So let's go back and see other types of sensors. Yeah.
Just one thing, just one small thing, sir.
Yeah, please.
This short term and long term. Short term means how much duration?
Short term means,
it would be okay.
Let's say we are doing some testing in the laboratory, 2, 3, 4 hours, maximum
Right.
6, 7 hours. That's short term.
Right.
But long term, even if
Okay.
you are leaving something for 1 week, after 1 week your results will not be reliable. You will see fluctuations in the measurements even if there is no additional loading. Okay, let's go to
Right. Thank
vibrating
you.
wire strain gauges. So now the vibrating wire strain gauges, they work on the principle of vibration. Vibrating wire strain gauge, it uses the vibration principle. So principle is very simple. All it does is that inside there is a pre-tension wire, and this pre-tension wire will have a particular natural frequency of vibration we know from physics. And then there is a vibration coil which plugs this wire into vibrations, and then the frequency is measured. So basically we know from physics that the natural frequency of vibration of a pre-tension wire is given by this expression. So here T is the tension in the wire, so we can express it in terms of strain, that it's basically strain multiplied by the Young's modulus, that gives us the stress, and if you multiply it by the cross-sectional area, that gives us the tensile force. Similarly, m is the mass per unit length, so all we have to do is we multiply with density, the cross-sectional area. So what happens is that numerator and denominator, the area of cross-section will get cancelled out, and we will be able to derive an expression for the strain in terms of the measured frequency f, and from the frequency measured we can obtain what is the strain in the system. So imagine that you have installed this vibrating wire strain gauge in your component, and at that time the component is not loaded but there is pre-tensioning in the wire. So you know that this is the case of zero strain, so you can find out how much is your reference strain in the wire by using this formula. All you have to do is just measure the frequency of vibration, and you have the constants like the density, the Young's modulus, and from this you will come to know what is the reference strain. Then after some time, let's say the component is undergoing some strains, it is under tension or compression. So what will happen if it's under tension? The natural frequency of vibration will increase, and if it's under compression, the natural frequency will decrease. So you have already measured the reference strain corresponding to the original frequency f0. All you have to do is that after the component or the host structure is under some strain, you measure the frequency again. Let's say it's now f1, and from the measured frequency you can again calculate how much is the strain. So this is basically strain in the wire. So earlier the strain was epsilon naught, and now the strain has changed to epsilon 1. So how much is the strain undergone by the component? Component will undergo the strain given by the difference of the two, right? So that's the principle we use for measuring of the strain. So it's very important that when the component is unloaded, that time you must determine the natural frequency of vibration. So that's very simple principle, and it has been extensively used for long-term monitoring. Now this is the difference between the electrical strain gauge and the vibrating wire strain gauge. So this is suitable for long-term monitoring. But long-term monitoring, what? Dynamic or static? Static. Why? Because it uses the principle of vibration itself. So there is a sensor coil, it has to be charged, it has to be, a button has to be pressed, of course it's automatic button, and then it measures the frequency of vibration of the wire, and then it goes, the system records that frequency, and from that it estimates. So all this process means you have to subject the wire into vibration and then measure its frequency of vibration. It takes finite time, so it cannot be used for dynamic, very high dynamic measurements. And even if we are able to have a electronic system which very quickly does these measurements, there will be interference from the surrounding noise, because you are measuring some frequency and the ambient noise is also dynamic in nature, so there will be interference. So it's good for static measurements. Now I'm just showing you two case studies. So one case study is from this bridge. This bridge basically connected Singapore and Malaysia, and this bridge was completed in 1997, and it was monitored right from the construction stage till many years, at least 6-7 years. The data was retrieved from the sensors which were installed in this bridge. So it had stress cells, vibrating wire strain gauges, and thermocouples. So the investigators, they were getting continuous data right from the construction stage. So they were specifically monitoring some of the segments, and they were able to derive a lot of information. So we'll just see very interesting information which they got.
Sir, actually, I have one question regarding these strain gauges. Sir, how these data are going to transfer to the computers or some receivers? Because are they means ki they are connected through wires or something else while concreting? What exactly is the connection between the sensor and the receiver or computer?
This is there is no lack of technology for that. If you are doing in the lab, you do a direct connection. For example, in our lab, we are doing direct connection from the sensor to our data logger. But at the site, these days cloud is used. So what they do is that they use a local small data logger, and that collects the data from the adjoining sensors, and then through the wireless technology, the data is transferred to the cloud. So that is the normal practice these days. Okay, but simple thing is that wire has to connect from the vibrating wire strain gauge to the immediate closest data logger. All right. Okay, now here we are showing some of the interesting observations. So here they were not able to measure the absolute strain, but they were able to measure the in a relative sense. Possibly they did not measure the reference strain. So that's why if you see here the strain values, they are just relative in nature. So what we can see is that as the curing is happening, you can see a decline in the values. So essentially here the values which are being reported, they are compressive in nature. So what we can see is that the compressive strain is declining. So that means curing is happening, and that's why when curing happens, what we see is that there are the development of tensile strains inside. So this gave the information that yes, curing is happening. And another achievement of the those investigators was that they could specifically pinpoint some of the important construction events. For example, now the casting was from two sides, and then this was coming, and finally when the two were stitched together. So what happens is that initially the behavior is like a cantilever. So cantilever means that we have the compression at the bottom and tension at the top. That was the behavior. And when the continuity stitch was done, then what happened that one can see the change in the relative positions. Now what was in compression, it has gone in tension, and vice versa. So this basically gave a very clear cut information that yes, now the continuity stitch has taken into effect. And then they also did the measurement of the temperature. So bottom and top temperatures, they were different. So all these measurements were taken, and that was the time when the structural health monitoring was just at the beginning. So vibrating wire strain gauge, of course, we have the wires to handle at least from the sensor to the immediately nodal point. Usually these days, if there are 5-6 sensors, they are very close to each other, then a common miniature data logger is installed near them, and then that is connected through the GPRS mode to the server, and it continuously sends the data. That's how these commercial products are available these days. But then there are wires are definitely there. Then it's suitable for measuring static strains because it uses the vibration principle. So when it uses the vibration principle, so first thing is that it cannot make very fast measurements, and then the other reason is that the surrounding ambient noise, those noise measurement will also interfere. So that's this point, the one related for the dynamic measurements, that because it's prone to noise, so that's why it's not good for dynamic measurements. And then if we compare the cost is very high as compared to the electrical strain gauge. So I hope you remember what cost I had projected for electrical strain gauge. It was close to 100 rupees, whereas here it's 7,000, 8,000, something of this order of the cost. So it's quite expensive, but yes, it is very good for long-term monitoring. Maybe 10 years is nothing strange if we are doing monitoring for 10 year plus.
See, these vibrating strain gauges which you have been explaining, if we start during construction stage, see, our motto is that the work going on should conform to specifications. So how, I mean, the construction is going on, we have already put the strain gauges. So, I mean, how we shall know that the work during construction stage through sensor is okay? That is my question.
Yes, so one example is already given here, that in the case of the bridge monitoring, the investigators, they could pinpoint all the major construction events. For example, the continuity stitch. Similarly, if we talk of, for example, multi-story building, and if we are installing these gauges at the bottom where the column is making junction with the foundation, and if we have these strain gauges over there, are multiple of them, and as the construction is going on, we'll be able to pinpoint the events. For example, when the first floor slab is cast, it will show change. Second floor, so each floor will see change, a noticeable change. So that way each and every construction event can be very easily monitored by these strain gauges. Now the other point is the quality of construction. That part, these sensors don't have the jurisdiction. So for that part, the prevalent procedures, they have to be used.
Okay.
Yes, so I am saying that this vibrating wire strain gauge is reusable, right? We can unmount it and mount it on other specimen also. But strain gauges can be used only once, right?
See, electrical strain gauges, they are bonded using adhesive. So if you, for example, want to take them out, so if you cannot take them out, the only way is that you have to tear apart your sensor. Now these vibrating wire strain gauges, if they are installed on a steel structure by welding, then they can be de-welded and they can be reused. Okay. Or if there is some other mechanical means, so they can be taken out and they can be again reused. But if you are inserting them inside concrete, you have bonded on the rebars and you have inserted inside the concrete member and then you have cast the member itself, then it will be not possible to reuse them. Okay, let's now see a dynamic sensor, accelerometer. So accelerometer, you all know the principle, the basically what is the construction of an accelerometer. It has a seismic mass and this is connected to a base mass by means of spring dashpot. So basically this base mass is well attached to the structure, and when the structure vibrates, then the vibrations are transferred through this spring dashpot mechanism to the seismic mass. So what happens here is that you have, in fact, in your dynamics course you must have solved this equation also, that if your base structure is vibrating with some acceleration and then your seismic mass is vibrating with some other acceleration or for that way displacement, then we can write the equation of motion for the seismic mass like this, because Here inertial term is contributed by the absolute acceleration, but then we have the other terms, the spring force and the damping force, they depend on the relative displacement or the relative velocity between the seismic mass and the base mass. So this is our equation, and it can be proved that if we have the frequency, the operating frequency very less as compared to the natural frequency of this system, because this system has spring, damper and mass, so we can find out what's the natural frequency of this system under root k by m. So if we are dealing with frequencies which are of much smaller magnitude as compared to the natural frequency of this system, then we have the acceleration, the absolute acceleration of the component or of the structure which is to be measured shall be directly proportional to z. And what is z? Z is basically the relative displacement between the seismic mass and the base mass. If you are able to measure the strain undergone by this spring, so that gives us a value of the acceleration. Alright, so this is under the limiting case. So this is the basic principle. So for that, it's very important that the frequency which we are measuring should be very low as compared to the natural frequency of the accelerometer assembly, else it will lead to erroneous results. So that principle we use, and today we have seen also this is basically the picture of the same cantilever beam. So here we have this accelerometer, and here the signals, they are first fed to a conditioning unit, and then they are taken to the oscilloscope, and today you have seen in our lab the obtaining of the signals also. And in the next lab that we'll be doing on Thursday, we'll send you some measurements to analyze. So accelerometer is what we are seeing is that it's a dynamic measurement device. So let's not compare directly with respect to the other sensors which we have just gone through today. So basically, if we are seeing from the point of view of the cost, its cost is very high. The type of high accuracy accelerometers, they are quite expensive, but then we have the MEMS type accelerometers. For example, even your mobile phone has an accelerometer which is MEMS based, and of course these will be very low cost, but then they are good for relative measurement. For example, if you are just wanting to measure the frequency of vibration, you don't need the absolute value of the acceleration, you only need the relative. So that way you can use the mobile phone, but the mobile phone accelerometer will not give you very high accurate values. So for that you have to use expensive accelerometers. Then they have a low bandwidth we have seen, because the frequency to be measured should be low as compared to the limiting natural frequency of the accelerometer assembly. Then they are very fragile. Even if they drop from height, they would malfunction. And then they are having large size also. Yeah, so they are very fragile, and because they are big, now you, for example, leave such accelerometer on a structure, and if you are just letting it go, it's not inside, it's outside, then they can face vandalism, or they can, because it's an expensive item, they can be stolen. All right.
One small thing comes to mind, which is helpful. Just one. Sir, this accelerometer, you talked about the limiting natural frequency.
Yeah.
I mean, in the description, what can you just further elaborate? What is this limiting natural frequency?
Yeah, limiting natural frequency is because inside we see there is a spring and mass. So under root k by m, that is the natural frequency of the system. So if we are using it for some measurement, then our measurement frequency should be at least 1/5 of the natural frequency of the system. Else the equation will not be valid. The governing equation will not be valid.
I see.
Governing equation is only valid when the impressed frequencies are the external frequencies which are acting on the structure, they are very small as compared to the natural frequency of the system.
So you said natural frequency is root K by M.
Yeah,
That's
of
how
the
we
accelerometer.
normally
It's
work
not
out.
the natural frequency of the structure. It's basically we are saying that the external frequency to be measured should be very low as compared to the natural frequency of the accelerometer assembly. Usually this is specified by the manufacturer. Manufacturer specifies okay that this is the range of frequency where this accelerometer can be used.
Right. Okay.
Okay. So, and
So
any
here
doubt
DVT
on the
means,
conventional
just,
sensors? Any doubt any class student has on the conventional sensors? If not, then we go on the sensors based on smart materials. So we now introduce the concept of smart materials. So these smart materials, these are specific materials which have the ability to change their physical properties in a specific manner when there is a certain specific type of stimulus. So you must have for example read in biology that living beings we show stimulus response. Any stimulus is applied, then we show response. So these materials, they also exhibit similar kind of stimulus response characteristics. Now this definition was historically adopted in 1988. That time there was a workshop in the US, and in that workshop the term smart was formally adopted by consensus that we'll use smart material, we'll not use the term intelligent materials, because intelligence is much higher level. So these are just smart, they are like the mechanical response that we apply a stimulus X and we see a response Y. So there are now several commercial type of these materials, and each of these materials like piezo materials, electrorheological fluids, shape memory alloys, optical fibers, they exhibit this stimulus response characteristics. For example, now this diagram shows for piezoelectric materials, if we apply stress, what we'll see the development of electric charges. Piezoelectricity, you apply a stress, they will just develop electrical charges. And then the converse is also true. You apply electric field and we'll observe here some mechanical deformation. And then we have the shape memory alloys. Shape memory alloys, you apply heat, you heat them and you will see some funny things happening. The memorization of the just hold on, the memorization of the previous original shape. Then there are electrorheological fluids. So if you apply an electric field, then their rheology is changed. They undergo change of the viscosity. That means the internal damping is changing, the stiffness is changing, and that has a lot of possible applications in structural engineering also. That when the external dynamic loads are acting on the structure, then by suitable changing of the rheology, the natural frequency can be adjusted away from the impressed natural frequency. Then optical fibers, each one of us knows how we are now getting the 300 Mbps network. It's through the optical fibers. So optical fibers, they are used for communication purposes. So they basically, how communication is done? Communication is done by means of light impulses. So light impulses, they are passed through these fibers, and this information is then converted into electrical signals at the end. So they can travel very long distances through the process of total internal reflection. And then in the defense field, there are these magnetostrictive materials that by application of the magnetic field, they undergo development of mechanical strain. So we'll just see how these materials, they behave one by one. So I'm just first showing you a video beginning with the piezo materials. So here the principle is illustrated.
When voltage is applied to a piezoelectric element, it contracts. A piezoelectric element and a vibration plate form a set. The contracting piezoelectric element moves the vibration plate to generate an inkjet mechanically with no need for heating. Each inkhead contains thousands of these sets, with each one firing precisely the right amount of ink at precisely the right place, more than 40,000 times a second, achieving fine, high-quality printing.
So this is the illustration of one application of the piezoelectric materials. So piezoelectric materials, we apply electrical field, they will undergo expansion or contraction. You reverse, so whatever was expanding, that will undergo contraction, and vice versa. So what they have displayed here is that if you bond a normal plate and then metallic plate with piezo, so application of this kind of potential difference or electric field, it will lead to bending, and that's what is used in inkjet printers. And now we just see here optical fibers. So basically here, by UV radiation process, these kind of gratings are created, and these gratings, they act as filters. So if we are passing light from one end, then what will happen? These gratings, they will act as filters and they will reflect a particular wavelength. For example, now light is going, and what happens is that one particular frequency is reflected back. This is the Bragg wavelength, and remaining, they are passing. So when the fiber is under stretch, what will happen is that this Bragg wavelength will undergo fluctuation, and this is used for strain measurement. Now here, this is the explanation of the electrorheological fluids. Now you see here that once an electrical potential difference is applied, the viscosity will undergo change. Now no potential difference, and after it is switched on, you will see there is some change. Now the potential has started to build up. Now potential is applied, and now the viscosity will undergo change. Now the viscosity has increased. So these are the applications, and then similar type of materials are magnetorheological or MR dampers, and they are now used in shock absorbers. Okay, now we show you about the shape memory alloys. And shape memory alloys, basically what happens is that, as the name suggests, if you are giving a particular shape to the alloy, and then let's say you crumble everything, after some time you can regain that shape by heating it above a particular temperature called as the transition temperature. Now here,
how a bird soars.
the application of the shape memory alloys in aviation technology is shown. Basically, we would like to have our aeroplanes in the way the birds, they use their wings. Unfortunately, we don't have that flexibility in our aeroplanes, because here right now, how the direction is maneuvered, basically it's by use of the hydraulic systems. But if we have flexibility of changing the shapes, then this would have been very easy. So we are just trying to show this through this video. I am just doing it fast forward. Yeah, so imagine if we had these kind of shape changes. So by shape memory alloys, it is possible. So right now, for example, how the maneuvering is done, these mechanical hydraulic operated systems, they basically are helping in the steering. So what happens is they are very complicated because a lot of moving parts are there, so they add to the weight. But if we have something shape memory alloys, automatically if the shapes are changed, then it would be easy, like this. But what is the shape memory effect? So now this is the wire, shape memory wire. This is its memorized shape. Now this gentleman, he is making it straight. and now he has a blower. So the moment he pumps in hot air, now see what happens. So the wire has completely got back into its original memorized shape. So this also has a lot of applications. So one application is this kind of jellyfish. So this is where basically using the shape memory effect. Alright, so I'm just closing this video. So we'll now one by one we'll study piezo sensors and the fiber optic sensors, because both of these, they are belonging to the smart materials club. So piezoelectric materials, basically they exhibit two phenomena. One is called as the direct effect and other is called the converse effect. Direct effect means that if you are applying stress, then what we see is we see the development of charges. Now when we are talking of stress, the stress has to be dynamic stress. Because if we are applying static stress, what will happen is that eventually the charge will dissipate, because you would definitely use some measuring system by which you are doing the measurement. So eventually the charge will dissipate. So they are very good for the dynamic systems like this. And if you are reversing the direction of the stress, then what will happen? The charge polarity will also reverse. Now they also exhibit the converse effect. That is, if you apply electric field, say dynamic electric field, what we'll see the development of strain field. So if we are applying for example an alternating electric field, we'll see this kind of vibration happening. So what is the application? Application is in vibration control, flutter control. So these are possible applications and they are used in the aerospace industry for that purpose. So direct effect means that we are applying some stress and we are just measuring the voltage across the patch, and that voltage is proportional to the stress applied. And for the converse effect, what we are doing is we are bonding the patch on some host structure, and then we are applying some kind of potential difference, an alternating voltage, and this makes the piezo patch vibrate and the vibrations are passed to the structure. So this is the converse effect. So in the next lab, Thursday, we'll physically display you the converse effect. Today you have seen the direct effect in terms of the vibrations. So that was, you are seeing the plot in the oscilloscope, so that was simply the use of the direct effect. But in the next lab class, we'll show you the converse effect also. So basically these piezoelectric materials, they occur in certain crystals. So these crystals are basically non-centrosymmetric crystals. So what happens is that if there is no elongation, then the net dipole moment is zero, but the moment there is some strain, then net dipole moment is developed, and that leads to the accumulation of the charges. So you can think of just like they satisfy the equations of the parallel plate capacitors. Like if you recall parallel plate capacitors, we know some basic equations from our school physics, so they satisfy those equations. So basically some of the materials, there are over 200 piezoelectric materials today, but first it was discovered in natural materials like quartz and like that. And now there are so many materials like lithium niobate is one material, then lead zirconate titanate. This is PZT. P is for lead because the symbol of lead is Pb, Z for zirconate and T for titanate. And then we have PLZT also, where another element is also added here in the alloy. So any question? Someone is raising hand.
Sir?
Yes, who is asking the question? Just introduce yourself.
Sir, let me tell Saket.
Yes, you ask the question.
Sir, is it sensitive to the polarity developed in the piezoelectric material, sir? Is it sensitive to the compressive or tensile stress developed, or it is the same charge, whichever type of stress that they are applying to the material, sir?
No, it will depend on what type of stress you are applying. So the charge will accordingly reverse. If tension you are applying, by application of the tension, we are seeing the accumulation of the positive on the top surface and negative on the bottom surface. So if you change it to compression, so these will be reversed. Okay.
Thank you.
Just one small thing, sir. You said the direct effect and the converse effect. This direct effect is sensors and the converse effect is actuators.
Yeah, exactly.
The actually physical thing.
Yes.
And then the converse effect actuator. Can you just further explain?
Yes, we are coming to that. So in fact, we don't visualize, but we are using the direct effect and converse effect every day in our life. Yes, so these are some of the applications of the direct effect. All the igniters, accelerometers, pressure transducers, tactile sensors, dynamic strain sensors, mobile phones, and structural health monitoring. These very applications, they use the direct effect. And converse effect is also used in mobile phones, fuel injectors, musical cards, printers. You have just seen one converse effect by the video which I showed you in the inkjet printers. In your mobile phones, how is the direct effect coming into picture? Basically, you are speaking, so these are acoustic waves. So by these acoustic waves, vibrations are produced, and these vibrations, they are converted into electrical pulses by the direct effect. So piezo transducers are there. And similarly, if you are receiving a call, so basically the other person, his signals which are converted to the electrical pulses, they are now reconverted into acoustic waves by the converse effect. And we have already seen in fuel injectors how they are being used. So today in the lab, I showed you some of the commercial types of piezo materials available. So the most popular piezo material is lead zirconate titanate. PZT is the most popular and the most versatile, I would say, and also very economical piezo material available today in the commercial market. And then among the polymers, polyvinylidene fluoride is very versatile and easily available. So the ceramics, they have higher strength, stiffness, but then they are brittle. They break very easily. So some of you who would be using these, you will have your first-hand feeling and experience of how brittle these ceramics are. And polymers, on the other hand, they are very shape conforming in nature. They can be easily bent, but then they have lesser strength and lesser stiffness. So the ceramics, they are suitable both as sensors and actuators. And as far as the polymers are concerned, because they are soft, so they are not very good as actuators, but they are very good as sensors. And then there are some special types, like we have seen Duract and the macrofiber composite. So this is a Duract. Duract I did not show you, but it's also similar to the MFC type. So MFC type can be very easily bent. So if you compare Duract and MFC, MFC has greater bendability. So let's now come into mathematics. Let's bring mathematics in our study. So let's just understand the constitutive relations which are followed by these materials. So imagine we have this kind of configuration, that we have a very small plate of piezo material and we are analyzing it like a bar. So it has small weight and it has length and it has a certain thickness, and we are subjecting it to an electric field, and simultaneously we are applying some stress also. So this is the condition. Though in actual practice it may happen that we are applying stress only and no external electric field, or vice versa. But let's say, for the sake of the complete understanding, let's do this. Then what will happen? See, it is just like any ordinary linearly elastic material, it basically exhibits stress-strain relationships, Hooke's law. So here we have the strain given by stress divided by the Young's modulus. Now here, if you observe carefully, you will see some difference. Here there is some superscript and there are some subscript also. So subscript is because it's a tensorial component. So 1 is basically signifying the direction. But then we have here an E. So E means that it is measured under zero electric field conditions. So this is the Young's modulus specifically measured under no electric field condition. So at the time of the measurement, no electric inputs were given to the material. And then there is a bar at the top. So bar means that it's a dynamic. We all know that Young's modulus is different. Static Young's modulus is different from the dynamic Young's modulus. So when some material is under dynamic conditions, then we should use the dynamic Young's modulus, dynamic stiffness. So it is that. So bar above a term signifies that it's basically a dynamic parameter. So we have this strain, but then because the patch, it is a piezoelectric patch, it's a piezoelectric material. So what will happen is that electric field will also give rise to some strain. So that strain is additional. So we have the stress induced strain and then we have the strain induced by electric field also. So it is given by this expression. So we have to multiply the electric field. So E3 is the electric field and we are multiplying it by this parameter D31. So what is D31? We'll just define it. But basically you may have guessed that these subscripts 3 and 1, they are very special. So what is 3 here? 3 is the direction along which the electric field is acting and 1 is the direction along which the strain is happening. So here it is 3, 1, but it can be 3, 2 also. If you, for example, replace the direction 1 by direction 2, that means that instead of applying stress along direction 1, you are applying stress along direction 2. So then this will become D32. So let's also see the other equation. So the first equation which I just showed, this is basically equation for the converse effect or the actuator. And the other equation which I am showing is basically equation for the direct effect. So direct effect means that first of all this behaves like a parallel plate capacitor. What happens in a parallel plate capacitor? Parallel plate capacitor, if you apply an electric field, it will undergo accumulation of the charges. And we are very much familiar with the equation Q equal to CV. Q equal to CV, we are very much familiar. So basically this equation D3 equal to epsilon 33, again we have a superscript and then a bar multiplied by the electric field is same. Because electric field and voltage, they are interconvertible. What is electric field? Electric field is basically potential difference per unit distance. So basically electric field is nothing but the voltage divided by the thickness h. And D3 is basically charge density. If you have the total charge, you divide it by the area, so that gives us the charge density. So this is the capacitive effect, that this behaves like a parallel plate capacitor. You are applying an electric field, so what will happen? Charges will accumulate. But then there will be another effect, that because we are applying some stress, so stress will also give rise to charges, and the expression is this. Again we have to multiply the stress by the same conversion factor D31. So now what is D31 called? So D31 is basically called as the piezoelectric strain coefficient. So this is basically the piezoelectric strain coefficient D31. And what happens is that if we are just wanting to use in the sensing effect, that means we are not applying any external electric field. So in that case, what will happen? Or equation number 2 will simplify. We'll not have the first term at all, and simply we'll have this charge density proportional to the applied stress. So it can be used for measuring the external stress. Or if we make use of the Young's modulus, then we'll be able to measure the external strain. So what we have done is that we have made use of this equation, and then we know that this external electric field is 0. So all we have to use it now, that we can make use of the parallel plate capacitor equation Q equal to CV, and we can derive this expression for voltage across the piezo sensor as function of the strain. So if we have the strain, and then by measuring the voltage we can measure the strain. So this gives a sensitivity of roughly 200 millivolts per microstrain. Means if your strain is 1 microstrain, that is 10 to the power minus 6, the piezo patch will display 200 millivolts, 0.2 volts. So this is very remarkable. This is very remarkable conversion factor. So now what you can do is you can just derive this after your class. So I just give you a hint. All you have to do is, in this equation we don't have any external electric field, so this term is gone, and this we can write as the strain. I'm using the symbol now S, multiplied by the Young's modulus, and so I am putting a bar at the top to signify that it's a dynamic measurement, and it's measured under constant or zero electric field. Then this is basically nothing but this is equal to Q by A. Q is the total charge, and you divide it by A, Q by A. So D3 is charge density, right? So its definition is it's Q by A. And now you can use the parallel plate capacitor equation. So substitute this by C into V. C is the capacitance, and what is the capacitance of parallel plate capacitor? You know that it's basically given by the electric permittivity of the material, epsilon, then the area, and divided by the height. So you just input this, and you will be able to derive this particular equation. Alright, so here now another point I want to highlight, that this is the electric permittivity. So this is the electric permittivity, and you see that there is first of all a superscript T. That means that it's measured under zero stress. So that means when we are doing this electrical measurement, the material was not under any kind of stress. So now you pay attention that for the Young's modulus we are measuring at zero electric field conditions, and the electric parameter we are measuring under zero stress conditions. So this is how these measurements are made. And again there is a bar. Bar means that this is also dynamic in nature. So the electric field is dynamic in nature. And how the electric field is related to voltage, it's just related by V by H. E3 is basically the voltage divided by the thickness. So you can derive this equation. Alright, so that's your homework. I've given you a hint.
Just one thing, a small thing, sir.
Yes.
This electric permittivity.
Yeah.
The E33. Can you just further say what is this?
Yes. We are coming. Now we are going into details.
Okay.
So first of all, let's visualize D31. So D31 is the piezoelectric strain coefficient. So here the first subscript, it tells us the electric field axis. So along which axis we were applying the electric field. And the second number here, it tells what axis, along what axis we are basically measuring the strain. So it can be D32 also, it can be D33 also. So what will be D33? D33 means that we are applying stress like this in this direction, and we are measuring the electric voltage also in the same direction. These charges are also accumulated on the same surfaces perpendicular to which we are applying the stress. So it can be D33 also. And then we can use this to define D31. So this equation, again I am asking, is this equation for the sensor effect or the actuator effect? This equation, is it the equation for sensor effect or the actuator effect? this is the equation for the actuator effect, that you are applying an electric field and this electric field is giving rise to strains. Alright, and this is equation for the direct effect. Direct effect means that we are applying some stress, and what we are seeing is we are seeing here the accumulation of the charges. Alright, so we can use these equations to define D31. So first equation, we can say D31 is strain per unit electric field under zero stress condition. So that means if the stress is zero, so this term is not there. So what is D31? D31 is strain per unit electric field. So all we have to do is, if we apply electric field and we keep the patch hanging, so it's stress free, and what we have to do is we measure the strain developed in the patch, so we can obtain the value of the D31. Alright, and we can use the other equation also to define D31. So can anyone guess how we can define D31 by using this equation? It is this. It is the charge density induced by unit stress under zero external electric field condition. So if your electric field external is zero, this term is gone, then what is D31? It is basically the charge density per unit stress. So apply some stress and find out how much the charges are generated, and that will give you the measurement of D31. So this is how experimentally D31 can be evaluated. So now we are giving you an exercise. So these are basically the parameters for this particular grade PIC 151. We have basically obtained from the site of the PI ceramic. So if you go to PI ceramic and you will get the data sheet. So for this values which are given here, you can find out, you can determine the value of the K yourself, the constant. I have already told you that it's 200 millivolts per microstrain. That is the approximate value. So if you input these values, you will be able to get the exact value. Now here, what is this? It has given here relative permittivity. So what is permittivity? Dr. Dhawan asked this question, so I think it must be fresh in your minds at least. So can you define what is electric permittivity? What does electric permittivity signify? See, it has to do with the parallel plate capacitors. So in the case of the parallel plate capacitors, Q is equal to given by C into V, and we can input here the expression for C. It is the permittivity into the area and divided by the thickness, or H, multiplied by the voltage V. This is how electric permittivity comes into picture. So all dielectric materials, they show this phenomena. You apply an electric field and they will show the accumulation of the charges. So that is the dielectric effect, and the epsilon term is basically the permittivity, the dielectric permittivity of the material. So all materials have different values. And does anyone remember the electric permittivity of free space or air? How much is that? Because most of the manufacturers, they provide this in relative terms. So it says that 2400 is basically the relative permittivity. Relative permittivity as compared to, relative to that of the free space. So does anyone remember how much is the relative permittivity of free space? So if not, you can just have a look in the physics book and find out what is the permittivity of the free space, and then you will be able to get the absolute permittivity. Alright, so all you have to do is you have to find this constant K. By this constant K, I mean this. So this defines the sensitivity. So what we can see is that the higher the value of D31, the higher the sensitivity, and similarly lower the value of epsilon 33, the lower the permittivity, then the higher the sensitivity. Okay, so for effective sensor, D31 should be very high and epsilon 33 should be low. Alright, so any doubt so far? Just you can raise your hand if any doubt so far. So if not, then I told you that we can have D33 also. What does D33 means? D33 mean that we have the stress is applied along the axis 3. Axis 3 is the vertical, means thickness direction, like this. So I am showing here the stresses, the tensile stress. That's why I have chosen this direction. It's different from the direction I had earlier shown. I had earlier shown compressive. So here, if you want to write the equation, the equations will be similar, but only thing is that in place of D31 there will be D33. Now what you see here, because here the stress is in the direction marked by 3 in the vertical direction, so we have this equation like this, and similarly the other equation will also change. So in both the equations the term D31 has replaced D3, and accordingly the stress has also changed. It's now T3 instead of T1. Now it is also possible, see here we are showing D31 and D33 effects separately. We have applied either the stress in the along axis 1 or we have applied along axis 3. But it is also possible that these can act simultaneously. So generally piezoelectric materials, they exhibit all the effects simultaneously. So if we are subjecting piezo material to a general stress, so all the effects will be combined. Alright. So generally D31 is negative. So what does negative means? If you, for example, you pick up the data sheet, you will find D31 is negative. That means if we have electric field in the positive 3 direction, means if our electric field is like this, then what will happen? Positive electric field will give rise to negative strain, means it will bring rise to compression. Okay. Now another question let me ask, how do we define the positive direction of an electric field? How do you define positive direction of electric field? Positive direction of electric field is defined as that direction along which a positive electric charge is attracted. Okay. So that is the direction of the electric field. That means the field is like this. So here there is a positive field here, positive sign is here and negative sign is here. So then that is the the positive direction of the electric field. We are applying the electric field such that here there is negative and here there is positive. So that is the positive direction of the electric field. Now D33 on the other hand is positive, means you apply tensile strain, or for that matter if you apply electric field in the positive 3 direction, like the one which I have shown, then it will introduce a tensile strain. Alright. Now you must be wondering that how strong or how weak these materials are. Now that's why I have brought here the stress versus strain plot of typical piezo material, that it is being stressed in this direction and then it goes to a peak. Now you notice how much peak it has gone. It has gone to a peak strain of 10 to power. It is how much? It is 10,000 microstrains. Because if you, it's 10 to power minus 3, so if you convert into microstrains, means 10 to power minus 6, then you will have to bring here 3 more zeros, so it will be 10,000 microstrains. Now how much is the strength of concrete in compression? Concrete is somewhere here. Concrete, if we know, it is 3500 in compression microstrain, 3500 microstrain in compression, 0.0035. So compared to that, piezo is very, very strong. It can withstand very high strains, compression higher than 12,000 microstrain, even 13, 14 or 15,000 microstrains in compression it can undergo very easily. Of course in tension, like concrete, Like concrete is weaker in tension, so in the same way piezo materials, they are also weaker in tension. They undergo less strain, ultimate strength in tension as compared to compression. But yes, compared to concrete, if we are embedding these sensors in concrete, so we are sure that they will not prematurely fail. They will undergo large stresses, and these, they have very high fatigue strengths also. So typically the linear limit is around 5000 microstrains. We have the linear limit. After that, non-linearity comes, and till 5000 microstrains, there will not be any hysteresis also. We are seeing some hysteresis because we have subjected to higher strains, but till 4500 microstrains, there won't be any hysteresis. Okay, now we are showing one comparative study, a very simple experiment done in our lab. So here we have this steel beam. It has these sensors. So we are just comparing the response of piezo sensor with electrical strain gauge. So I had told right from beginning that electrical strain gauge, they are not suitable for dynamic measurement. So theoretically they can be used for dynamic measurements, because what we are measuring? We are measuring electrical resistance. So it's not very difficult to measure electrical resistance, very small interval. We can very easily measure at very small intervals. We can measure 50,000 samples or even mega samples per second. It's not very difficult. But then what is the effect? You see here we have the piezo sensor. This is the plot of the piezo sensor, and here we have the plot of the electrical strain gauge. Now can anyone comment what is the difference between the two, piezo versus electrical? And any comment on the nature? Basically these, they are representing the damped free oscillations, that you have excited the cantilever into vibrations the way we were doing in the lab today, and then we have left the vibrations to die. So do you notice any difference? If anyone would like to comment, please comment on this.
Sorry, in piezoelectric sensor there is a damping.
Damping is there in the electrical also.
Not as much piezoelectric.
See, damping is there.
There is already some strain goes.
So what the observation people are saying, that we are not seeing damping in the case of the electrical strain gauge. See, damping is a material property. It is basically the damping of the aluminium bar. So it will be there irrespective of the sensor. But thing is that it is not visible to that extent in the electrical strain gauge, but in the case of the piezo sensor, it's very evident. So what's that property of the piezo sensor which is making it exhibit, but it's not coming out in the case of the electrical strain gauge? It's the high signal to noise ratio. Signal to noise ratio is very high in the case of piezo sensor. So basically we were doing the measurement like this, that we started taking measurement at 0 time, and then at click of say 1 second we have hit the cantilever beam into vibration. So this is what happens, that strain is high, and then slowly the vibrations, they die down. So this process can be very easily captured for a very long time. It is so clean. But see, in the case of the electrical strain gauge, even if we are not applying any signal, still we are getting some noise. This is noise because there is no signal here. We have not hit the cantilever, but still some readings, they are being shown. So that is noise. And when we are hitting, then there is some signal, but signal noise ratio is very poor. Alright, so we are just showing here closely. Now see how clean is the signal to noise ratio in the case of piezo. See, even in the case of piezo, when you are not measuring anything, some signals will definitely be there, because that is because of the electrical noise. But then the moment the signal is there, signal has very high value as compared to the noise, so noise gets hidden. So this is more clear. this is clearer once I show you its time to frequency domain change. So this is, if we have this data, and if you do fast Fourier transform, those of you who have done say machine foundations course, you can do on MATLAB, change from time domain to frequency domain the way we have learned in your structural dynamics, and it will be like this now. So what we see here, this is the main peak, and then we see here small peak, and this is the line frequency 50 Hertz. So around 50 Hertz there is small peak. So why this is coming? Because there is bound to be some noise on account of the line frequency is 50 Hertz. So if we are not taking any measurement, we are not applying any signal, still some fluctuations will happen in the oscilloscope. Even if you pay attention to this in your next lab, that we will show you the oscilloscope, even if when we are not applying any signal, we are not making the cantilever vibrate, still it will show some reading. So that is the noise, and if you find out the frequency of this, it will come out to be line frequency, that is 50 Hertz. So this is what is this line frequency is visible here, small peak, but here the signal is distinct. So that is the main beauty of the piezo sensor, and it's not there in the case of the electrical strain gauge. And here we are comparing piezo versus accelerometers. So of course, if you compare piezo versus accelerometer is more standardized and more accurate, and of course the two are giving us different readings. Accelerometer is giving us acceleration measurement in meter per second square. Piezo is giving us voltage output in terms of volts. But if we are not interested in the absolute magnitude, but if we are just interested in the frequency analysis, then we are not bothered much about this amplitude. We are more bothered about the particular frequency we are trying to measure. So that way both are fine. But among the two, if we assign a score of 100 to accelerometer from point of view of the dynamic measurements, then piezo will also get a score of at least 90 to 95. Okay, and what distinct feature here is the cost. That in the case of electrical strain gauge, from dynamic measurements we get burst response, and of course from static measurements also, if you want to make long-term measurements, then electrical strain gauges, they are not reliable. We have seen it. So we get best response in the case of accelerometer, but accelerometers, they are very expensive. Now here the trade-off is offered by piezo sensors, that piezo sensors, they are very low cost and their quality is almost of the same level of accelerometer. Okay, so what we have done in our lab, we have minimized the use of accelerometers, and mostly we are doing all our experiments with with piezo sensors, all dynamic measurements. Now here we are showing the example of sensing flexure. Now you see here this setup. So what we have done is we have installed one piezo patch on the top, one piezo patch on the bottom. And what we have done is that we have connected them in this kind of arrangement. So what will happen is that if you apply a load down, when the beam is going down, at that time there will be compression in the top fiber and tension in the bottom fiber. So the charges will be different. For example, the top patch, let's say the upper outer surface has positive, but in the case of the bottom, outer surface will have negative. So then we connect them in such a fashion that the combined voltage output is additive in nature, something like this. So what we are getting is, we are getting the summation of the voltages of the top and the bottom. Now this is very important because this gives us a measure of the curvature. Because if we have linear strain profile, and if you are measuring the top and the bottom voltage combined like this, so this combined voltage is giving us a measure of curvature. Because what's curvature? Curvature is basically this angle of the strain profile with respect to depth, that is curvature. And what is that? This is simply like in the RC design also we study that it's basically the sum of the top and the bottom strains. One is compressive, one is tensile. So basically we are adding the absolute values, we are ignoring the sign, and we are dividing by the depth of the cross section, so that is giving us a curvature. So here what we are getting from the measurement, the voltage is proportional to the sum of these two. All we have to do is just measure whatever voltage we are getting and divide it by this constant K, and also divided by D. If you do this, you will get here the absolute value of the curvature. So this is physically possible in theory. And from the dynamic measurements, we will not get the static curvature, it will be basically the dynamic curvature. And then these are some of the devices which we can use. In today's lab, you saw oscilloscope of Tektronix. They have lifetime warranty, and at least our oscilloscopes are more than 12 years old, working fantastic. Then this digital multimeter, the digital multimeter in our lab, we have the older one, at least 17 years old, still working like a strong horse. And then other this is an Indian product, Quasartech. This right now we are not using. And then this is a very modular, very sleek multi-channel data acquisition system manufactured by Agilent Technologies, now Keysight Technologies. So we have a lot of products in the market by which we can very easily measure the strain, and if we have the dynamic strain, we can get the curvature. So different data acquisition systems, they have different sensitivities, they have different resolutions, and they have different functions and cost, etc., and sampling interval, etc. So typically this one is very sleek, and it has 64 channels, and it has a capability of 3 mega samples per second per channel. Maximum sampling rate it can go. Oscilloscope can go up to giga samples per second. So now we come to structural health monitoring. So structural health monitoring, and if we are using piezo sensors, we'll focus a little bit more on the piezo sensors, and then we'll come to fiber optic sensors. So one effect is the direct effect. So direct effect is used as sensor. Other effect is basically if we combine the direct and the converse effect, we can use it as a technique called as the electromechanical impedance technique. So we'll give you an introduction of this technique also today. Of course, we'll go into depth of each and every of these aspects in the forthcoming lectures. So this lecture is basically giving you a picture of the entire thing. Okay. So then these are concrete vibration sensors. So here these sensors, they are basically making use of piezo inside concrete. Today I did not show it, so just give me a minute, I'll just show you it. They are in my office right now, in the office. So I'm just taking a break of few seconds. Yes, so I have this sensor. This is the concrete vibration sensor. So let me just make myself spotlight myself. Yeah, so this is the concrete vibration sensor. So this has the piezo element inside. So advantage is that we can very easily embed it inside concrete. Anytime during the casting process itself, this can be made to have an effective bonding with the surrounding concrete, and then this can be used for monitoring the structure for long term. So we have given the license to Central Electronics Limited to produce these sensors. So here now in this slide you see here the concrete vibration sensors. They are now embedded, and once they are embedded they become permanent part of the structure. So here we are comparing with the surface bonded piezo patch also. So surface bonded piezo patch has issues that it can undergo some deterioration or damage because of the environment or other reasons, but those which are embedded, they can last for a very long time. So here we are comparing the response from piezo with that from the accelerometer. Of course, the two are providing different parameters. Accelerometer is providing us acceleration, meter per second square, and piezo is providing us voltage in basically volts. So but what we are comparing is the frequency response. So this is from the accelerometer and this is from the concrete vibration sensor. So concrete vibration sensor, it has excellent signal to noise ratio because it's embedded inside, so it's very safe, so no chance of any damage. Let me now exit the spotlight so that we focus on this slide. Yeah, then because it's inside, so it has higher longevity also. It has very low cost as compared to accelerometer, miniature size, and then there is no frequency limit. See, in the case of the piezo versus accelerometer, we have to have low frequency. If you want to measure any frequency, then the frequency should be very low as compared to the natural frequency of the accelerometer assembly. But in the case of piezo, we don't have any limitation. As long as your data acquisition system can measure the electrical signal, high frequency electrical signals, so it's not a limitation from the material side or from the device side. Okay, so any doubt on the piezo sensors? We have finished the piezo sensors and now we are going into fiber optic sensors. Any doubt? Okay, let's visualize the fiber optic sensors. So basically, as I showed you in the video, the fiber optic sensors, they basically use these kind of UV rays to write here some gratings. And what are gratings? Gratings are basically filters. So if a wideband light is passed, white light, for example, white light, it has all the colors. So if you are passing white light from one end and then they are passing through these filters, then what will happen? A particular frequency will be reflected back. So this signal will be reflected back and remaining signal will be transmitted. So this particular frequency or particular wavelength, we are giving it a name. So the particular wavelength which is reflected back, we call it as Bragg wavelength. And this Bragg wavelength is very much dependent on the periodicity of these gratings, because we have created these gratings and the filters, and we can choose the linear distance between them, and by this we can tailor-made our fiber such that it reflects a particular wavelength. So this is the expression for the Bragg wavelength. It's given by 2 multiplied by the periodicity. Here this lambda symbol is the periodicity and n effective is the refractive index, the relative effective, the refractive index of the fiber Bragg this cable. So basically these, what are these materials? Fiber optic materials. Any guess what are these made up of? These are basically glass. These are essentially silica, made with silica, and basically if you see them, they are just like glass. For example, if you cut the fiber optic cable, if someone has installed the fiber optic cable in your home for internet connection, and if you happen to see a small piece and if you remove the upper coating, at the end you will, inside the core you will see a glass. So essentially these light signals, they are transmitted by glass, and through the process of total internal reflection they can travel very long distances. Say from India they can travel up to USA. Of course in between amplification will be required, but this is how they work. So now this if there is any perturbation in terms of strain, temperature or pressure, what will happen is the Bragg wavelength will undergo change, and this change in Bragg wavelength will provide us an indication of any external perturbation happening. So we can measure by this the strain, pressure or displacement. So there is an animation we are just showing you. Now you see this animation. So let's say this fiber is bonded on the top of the structure, and if the structure is undergoing tension, what will happen? The Bragg wavelength is increasing. So if there is a tensile strain, Bragg wavelength will increase, and if there is a compression, Bragg wavelength will decrease. So that's how very simple we are measuring the strains using Bragg wavelengths. So these are we call as fiber Bragg grating, because here there is a grating, and fiber because these are the glass fibers, and Bragg is the name of the person who invented these. So on his name the name FBG is there. Now the advantage is that in the case of the electrical strain gauge or other sensors, I said that if you have n sensors then you will need n wires, at least from your sensor to the nearby data logger. But that problem is not there in the case of the optical fiber sensors, especially the FBG. Now all FBGs, for example, if in your structure you have 50 sensors at different locations in your structure, you have installed 50 sensors, then all of these you don't need 50 wires. All of these they can be just installed along a same fiber. So you have just one source of light which passes and it scans through all the different FBGs, all the gratings, and at the end you have the complete data acquisition in terms of the recording. So that is possible. So this is the beauty of these sensors. So it has multiplexing potential. We call it as multiplexing, that along the same fiber n number of sensors they can be made. Alright. Then they have very small size, they are lightweight. So small size lightweight means that they are immune from wear and tear and other kind of damage. Then they are immune to electromagnetic interference. This is another point. All other sensors which are using electrical signals means basically if there is any electromagnetic equipment operating nearby, they will show some fluctuation. For example, you are doing measurement with piezo sensors, and if there is a strong electromagnetic field imposed by some equipment nearby, then you will have some fluctuations. But these fiber optic sensors, they are totally immune from any kind of electrical interference, because they are not using any electrical signal, they are totally using light. So that's how they are preferred in communication also, because the signal is light signal. So irrespective of any electromagnetic interference from anywhere, the signal will not be affected. Okay. And there is no problem of decay, because here the information is wavelength encoded. We are just measuring the wavelength. We are not measuring the peak value. As long as we are not interested in the peak value, we are only interested in the wavelength. So there is no issue, even if there is a decay. So limitations are there. So one limitation is that we are just relying on a single fiber, and if that fiber snaps somewhere, then all the 50 sensors, they are lost. So this is basically one of the drawbacks, that it offers us the multiplexing flexibility, but then this we have to be very careful. And then because they are using the light transmission principle, so the measurement system, the interrogation system, they have right now limitations in the frequency. Maximum I think they can go to 10,000 hertz or 10k frequency they can go. Of course, newer and better interrogation systems are also coming to the market, but this is a limitation for the dynamic measurements. Now here we are showing some of the measurements. So here we have installed these on a rock sample. This is a rock sample granite, and then this is the electrical strain gauge. This is a very long electrical strain gauge, much longer than what I showed you in the lab. In the lab I showed you very small one, but this is very long. And these are the fiber optic sensors. So usually for fiber optic case, two sensors are used. One for just temperature compensation, because if the temperature fluctuates, then also the Bragg wavelength will change. So to remove that error, one sensor is just installed, just weakly connected to the structure. And here these are shown installed inside concrete and attached to the rebars, static tests. And this is one of the early tests in the field of the FBG sensors. And then this is a dynamic test, comparison between accelerometer and these fiber optic sensors. Now when we say structural health monitoring, what do we expect? Now we are coming to the close. Basically in this lecture I have presented you a synopsis. We'll be going into depth of each and every aspect we have learned today. So basically we want to know, has any damage occurred in the structure after its construction? If yes, where is the damage location? If damage location is known, then next obvious question will be, how severe is the damage? And if these questions are answered, then last question would be that what is the remaining life of the structure? So these are the questions we expect from structural health monitoring. Now when we say non-destructive evaluation techniques, they are local. So if we are using a ND technique continuously, then that also becomes structural health monitoring, provided it is a continuous monitoring. But these ND techniques, if we use a particular device, then they work under certain conditions. Say if we know the expected location or something guess we have, then we can apply them selectively. Now when they are being used, that time structure is also unavailable and they are suitable for specific applications. So local techniques, ND will have a lecture and will study in detail the various ND techniques and what are their advantages and disadvantages. So when we say structural health monitoring techniques, and if we say global techniques, then I'll just illustrate you the principles. What are the principles? So one simple principle could be that we apply loads and we measure the deflections, and from the deflections we work out the structure parameters. We identify its stiffness matrix. So it's like inverse problem. So this is theoretically possible, but then static measurements, they are very difficult, because static measurement means you have to apply very large loads, then only you will see measurable deformations. So practically these techniques, they are not successful. So similarly we have dynamic response techniques. So dynamic response techniques, they are easy, because for making something vibrate, you don't need very high force. If you are, for example, walking on a pedestrian bridge, like foot crossover bridge, just jump on the top of it and you will make the structure vibrate. So this is a very practical solution, that by small force, a dynamic force, we can make a structure vibrate and we can try to get its model and structural parameters. Or alternatively, we start with a finite element model, do some dynamic test on the structure, and then do model updating. Model updating means fine tune your finite element model so that its response or its prediction matches the test you are doing. Now I give you an example. This was a bridge, and this case study is reported by Brown John. So this was a military bridge, and it was quite old. So the authorities wanted to increase its capacity, because the military vehicles which were plying, they had increase in the loads. So they came up with a solution that let's convert the support conditions from pin-pin to fix-fix. because what will happen is that this will increase the capacity of the bridge. So for that purpose they did a lot of construction, but after the construction they were not sure whether the fixed conditions they are successful or not, is there really increase in the stiffness. So for that purpose they use the global dynamic techniques to get the answer. So they installed accelerometers, and of course they installed some demountable strain gauges also, and then they found from their measurements they made some observations which strengthened the belief that yes, retrofitting is successful. So basically they made a model of the bridge, and then based on the measurement, the experimental observations, they fine-tuned the model, and their observations were that there was definitely a change, because they had modeled the ends like springs, and they could find from the measurement, they could find that these springs, their stiffness was 108 Newton meter per radius, and this is large enough. And they could also find that the natural frequency of vibration rate increased from 6 Hz to 8 Hz. So definitely there was an effect of this rehabilitation. So this throws the light that for rehabilitation, if we have done, then if we at the end of the rehabilitation we want to ascertain whether rehabilitation is successful or not, then structural health monitoring is very good. So the global techniques, especially the dynamic techniques, they are very practical. They help in quick assessment of the health of simple structures, but then they rely on few modes because they are global. So rely on first few modes. So by global dynamic techniques we can measure first mode. You see, every year we do experiments. After 2-3 attempts, students are able to obtain the first mode shape, but then the second mode shape is difficult, third mode shape still difficult. So as we go higher mode shapes, we encounter difficulty. So these rely on first few modes only. So that's why first few modes, that means they are low frequency modes. So they are global modes. So they can detect global level damage, or if the damage is large enough, but they are not able to detect very small or very fine damage. So these techniques, they are global dynamic techniques, they are insensitive to these local or incipient damage. So for local damage, we have a technique called as electromechanical impedance technique. So this is also vibration technique. Its principle is same, but its sensitivity is just like the local NDE techniques. For example, the ultrasonic technique, it has high sensitivity. So here the EMI technique also has high sensitivity, and here piezo materials, they are used as the key element. So we'll just see the principle. So here what we do, we have bonded piezo on the structure, and now we are applying some external electric field. So by direct effect and the converse effect, both will act together now. Converse effect in the sense that when we are applying an external electric field, this will make the piezo vibrate, and when it's vibrating, it will interact with the structure. And then the response of the structure will again affect the current flowing through the circuit. So now it's the direct effect. So first, by converse effect, it makes the structure vibrate, and then it collects the response by the direct effect. So here the piezo is vibrating, so it vibrates with the structure, and then the response of the structure itself represents in the current flowing through the circuit. So what we are doing is we are measuring the current flowing through the circuit, and then if we divide current by voltage, what we get? Voltage by current is basically impedance. So current by voltage is basically the admittance, and we do this measurement using the LCR meter. Today in the lab I showed you LCR meter, so we do this measurement using LCR meter. And because there is a phase difference, see, always dynamic phenomena, there will be phase difference. Even in the LCR circuit, we see that that is the main point we study in the LCR circuits, that there is always a phase difference, L, C and R. In one component, the current and the voltage are in phase, the resistance. In the case of inductance, the voltage leads the current by 90 degrees, and in the case of capacitance, the voltage lags behind current by 90 degrees, right? So similar phenomena occurs here also. There is a phase difference between current and voltage, and we measure it and we find that it is because the phase difference is there, so naturally we have the complex algebra coming in, so it has real and imaginary parts. So here the piezo patch is acting as sensor and actuator simultaneously. So what we do is that we apply this kind of sweep signal. So this LCR meter is capable of doing this kind of sweep measurement. It applies and then it makes measurement at all frequencies, and we get this kind of collection of all the data points in the form of a signature, and signature gives us the condition of the structure. So it's like your thumb impression. As long as there is no damage in the structure, your signature will remain same, and the moment there is a small damage, the signature will change. So it's just like your thumb impression, fingerprint. So this is where the EMI technique is used. So in contrast to the global techniques, is very highly sensitive. Maybe we'll show you one live demonstration in the next lab class Thursday. So this impedance based measurement is called as piezo impedance transducers, or the electromechanical impedance technique, because the word impedance is there because here we are measuring the electrical impedance, and that in turn depends on the mechanical interaction of the patch with the structure. So we have one lecture completely dedicated to this technique. So it's very low cost. The piezos, they have fast dynamic response, long-term durability, they show competitive performance, negligible aging, they have very high sensitivity, and now same patch, it can be used for dynamic strain measurement also, and there is no frequency limitation here. So this uses very high frequency in the kilohertz range, so that's why this technique is immune from the ambient noise, because ambient noise is generally in the low frequency ranges, say 10 hertz, 20 hertz, something like this, or maximum 50 hertz, or even the line frequency is 50 hertz. But the frequency which we measure from these EMI electromechanical impedance transducers, it's of the order of kilohertz, 100 kilohertz or something. So that's why it's immune to noise. So basically we have today covered a synopsis. So don't worry. As we go in the course, everything will catch in detail and study, but this was also necessary so that you have a complete picture of the various sensors and various systems, and then we can perform experiments also. So now today you had the lab, you had some physical feeling, and now you are studying in the lecture, so you will have greater feeling, and then again you come back to the lab next. So that way we have given a synopsis of all the sensing techniques or the sensors in this one particular lecture.
See, friends, Bala has explained so beautifully the type of sensors, how we use. The primary objective is that how to, detect whether damage is there or not. With this, we see the baseline, and then if there is any variation in that, so the damage, the type of damage, and the location. And then further we can go to the remaining life of existing sections. This is a very interesting subject. Don't miss any class. And still, if you feel that any problem, I am there to help you, because I have actually used in my research projects the EMI techniques, where I could find out that from the baseline, if the signature changes, what would be the stiffness loss with respect to time, the damage, what would be the mass loss, and what would be the capacity loss. So, with the damage, you can detect the exact type of damage, the location, and then if you know the timely, then we can put the corrective action, and then can make the sector safe. From damage to the failure, we can go to the back thing, and we can make the sector safe by retrofit or by other means. This is what I would like to highlight further.
Okay.
Thank you.
Thank you, Dr. Dhawan. So thanks for bearing, because this lecture I have hold you for 2 hours. Whatever we have discussed today was a synopsis, and in the coming lectures we'll go threadbare in each of these techniques. First global techniques, then DMI technique, very threadbare will go. So we'll go in very detailed and very slow manner. And very slow manner.